Hello everyone, I'm Vaibhav Gupta, and in this video, we'll be going over the introductory concepts in the quantum computing space. So let's get started by reviewing the basics of the quantum mechanics. For this, we'll go back to our high school physics concepts, and especially we'll be going over the Young's double slit experiment. If you remember the setup of the experiment, it looks something like this. Whereas to have a light source which used to fire one photon at a time, and will place two slits, S1 and S2 in front of it. Then we'll place a detector D at the back. So this experiment is run in three phases. In first phase, we'll cover the slit S2, we'll observe the light pattern through S1. Then we'll cover the slit S1 and we'll observe the light pattern through S2. And after that, we'll not cover any of the slits and we'll see what happens when both of the slits are open. In this slit, the distance between S1 and S2 are a few millimeters. And one more important concept is we have to understand that a light doesn't propagate in the same direction. Let's say we have a very good light source and it's the propagation of the light will look something like this. And why is that? It's because of the Heisenberg's uncertainty principle, where we say since we know the momentum of our photons, there's going to be uncertainty error in the position of the photon. So the propagation will look something like this. And with these concepts in the mind, let's run our double slit experiment. So if my S2 is closed, my pattern will look something like this. This is it is very intuitive with the maximum intensity near S1, and the intensity decreases as we go as far from the S1 in a normal distribution. We'll observe the similar pattern where we'll cover the S1 and my S2 is open. So if I say that now my S1 and S2 are both open, intuitively what should happen is my pattern should look something like this. With both of the patterns, it should look something like with the maximum intensity in the middle of S1 and S2, and the intensity decreases in form of a normal curve as we go far from S1 or S2. But interestingly, what happens is when both slits are open, we observe the pattern on the detector, something like as you can see on the screen. Now, instead of this pattern, what we are observing are the rings. From this view, these rings are with some light spots and dark spots. So this pattern is strange, isn't it? And let's understand why, and let's understand how we can explain this situation. For me, it looks like the photons are somehow aware about whether the second slit is open or not. And it behaves like there are two of them instead of just one photon. So how we can justify a situation where we are saying that they are behaving like two photons instead of just having one photon? And now, as we cannot discuss or consider as such a thing as position or a coordinate of the photon, instead, what we're going to say is that there is some kind of probability distribution of the position of the photon, which which means that uh, which means that the photon can be passing through S1 and S2 at the same time with the probability of alpha with the probability of alpha of passing through S1 and the probability of passing through S2 as beta. So now what we have done is instead of defining the coordinate of a photon, we are considering the two paths. One path is going through the upper slit, the other path is going through the lower slit, and the photon is having some kind of probability distribution of its position. And this probability distribution is what we call the wave function. So my photon is behaving like a wave where it can pass through both S1 and S2. And it is collapsing when it falls on the detector. Uh, this wave function is going to collapse to one output on my detector, and that output will be the zeros where it will have where my both the S1 and S2 photons get superimposed. The superimposition we'll discuss in the later videos to give they get superimposed to give me the black rings, and the other output are the light rings. So so now we just said that the photons are going to collapse when we observe the output on the detector. Someone might ask a question like, is there any condition where they might not where they might not collapse? Certainly there is. So for that we have to take a black box. Let's make a black box with the black color. And this is a very confined black box with no interaction with the outer surrounding, with the outer environment. And in fact, the experiment inside the black box is not going to interact with even the walls of the black box. So this is my confined box out there. And I'm going to run that experiment inside the box where I have my light source, two slits, and a screen. Yes. Or let's remove the screen for a while. So in this, my photon is behaving like a wave function. So if this is my slit, upper slit, and this is my lower slit, so my wave, my photon is P, it's going to look something like, wave function is going to look something like it has both of the upper slit and the lower slit. And the probability going through the upper slit is alpha. The probability of going through the lower slit is beta. This wave function is going to exist as it is from the outside, since we can't see what's inside this black box. And I'm an observer here. So my photon is passing through the upper slit and the lower slit at the same time. But let's say I place a detector, a small one here. And I also have an observer inside. Let's say we have a cat inside. It's not a pretty cat, but still it's a cat. And when my photon passes through my lower slit, it lights up the detector. But after watching the detector, my cat dies. But if my photon passes through the upper slit, nothing happens, as we are not going to we have not placed any detector. So now my function is not going to collapse, and my observer, this cat, is not going to see anything. For me outside, this is still a black box. So I can't see what's happening inside. So for me, my cat is dead and alive at the same time, because the wave function of wave function of photon passing through the upper slit and the lower slit is existing at the same time. So now my updated wave function for the observer outside will look something like this. My cat is alive and happy if it passes from the upper slit, plus my cat is dead if it passes through the lower slit. For me as observer outside, my cat is dead or alive at the same time. And it is going to collapse only when I open this black box and see inside what's happening. Now, one more thing, my cat and my wave function are now kind of entangled. We'll understand the entanglement in the upcoming videos, but what it means is if my photon is passing to the upper slit, my cat is alive. If my photon is passing to the lower slit, my cat is dead. So these two instances are entangled with each other. So this is the basics of the quantum mechanics. After that, let's go over the minimal computation unit of the quantum computing, which is called qubit. As in the classical computing, we define a bit, and we define a state where it's like a bit can store 1 or 0. Similarly, in quantum computing, we can have an electron spin as a qubit, where we define clockwise movement, clockwise rotation spin as 1, or anti-clockwise rotation as 0. We can even use photons, as we discussed earlier, as a qubit, where we can have the vertical propagation as 1 and the horizontal propagation of the photon as zeros. Or in fact, we can even say, as we discussed, like the going through the upper slit as 1, going through the lower slit as 0. So we can have propagation or the position of the photon as the qubit. And the third one is the superconducting metal, where we can define the magnetic influence and the magnetic direction of the metal as 1 or 0. So after this qubit, how if we have to give a mathematical notation and definition to the qubit, let's see how we can do that. So let's say I'm defining my qubit as phi. My notation for the qubit, we can use either the direct notation, or we call it as a bracket notation, where this is the ket and this is the bra, and let's say x, y. So this is this is how we define a qubit. And to give a more mathematical definition on the qubit um, qubit is a unitary vector in a two-dimensional Hilbert space. So first, what I mean by Hilbert space is, I'm not going to go over the detailed explanation of the Hilbert space, but to give you some intuition, Hilbert space is a linear space over some field with a dot or in a product. In this video, we are going to consider the finite dimensional spaces over the field of complex numbers. So so I'll have two vectors in my Hilbert space dimension. Sorry. So I'm going to have my vector defined in a two-dimensional Hilbert space. And the second thing that we have to consider is it's a unitary vector. So if you can see on the screen, I can define my qubit as alpha of 0 plus beta of 1. What's the 0 and 1 here? These are the orthogonal bases. We can define anything as 0 or anything as 1, as long as they are orthogonal to each other. Here, we are defining the horizontal, let's say for the photons, we are defining the horizontal propagation as 0, and we are defining the vertical propagation as 1. In the classical qubit, either 0 will exist or 1, but in our quantum computing space, anything between 0 and 1 can exist. So we define as alpha the probability of occurring of the photon taking 0 as alpha, the probability of photon taking 1 as beta. So my wave function will look like alpha of 0 plus beta of 1, where it can take any value between alpha and beta. Sorry, between 0 and 1. So since it's a unitary vector, the probability the the summation of the probability will give me 1. And we can even change our orthogonal vector to something like this, the +1 and -1, where my +1 is when it makes a 45-degree angle here, and the probability of 1 and 0 are same, which are √2. And my -1, let me use a different color. And my -1 can be here. So it depends on us to choose the orthogonal basis. But here, what I want to emphasize is on the superposition. So what superposition m- means is that my physical system may be in one of my many configurations simultaneously, where the amount of each configuration is defined by a complex number. And these complex number are what we defined as alpha or beta. I know this is kind of a complex, these are kind of the complex concepts to go over the first time, and these are not that intuitive. But I hope that it gives you some intuition and some basic ideas of how we are going to define qubits and what a qubit is. In the upcoming videos, we'll go over the detail on the basic principles that defines our quantum computing space. So thank you all, and I'll see you in the next video.